let us begin. So the objective of this video is essentially to introduce what is linear regression, or what is regression in general in machine learning. We'll start off with just simple linear regression, and then the plan is to have a series of this where we move on to multiple linear regression and other types of regressions, such as polynomial, logistic regression, and lasso and ridge. But this one is just for simple linear regression, right? And we are also going to speak about how we evaluate essentially a regression model using residual analysis. Okay, so before we jump into it, I think it's always great to start off the assumptions of linear regression, the assumptions that we make in order for us to use linear regression. The first one essentially is the homogeneity of variance, otherwise known as homoscedasticity, right? And essentially this means that there is no relationship between the prediction error and the independent variable. All right. If those words seem like foreign to you, we'll discuss them in the slides. All right. So I'll tell you what an independent variable is and what the prediction error is. So in continuation, the error is not influenced by the independent variable, such that as we increase or decrease our independent variable, we should not see any change in the variance or across the invariant variables. We should not see any change in the errors as we increase or decrease or change our independent variables, right? So there shouldn't be any relationship between our error and our independent variable, right? And another important assumption is the independence of observations, right? So we assume that the observations are independently and identically distributed, right? So that there are no hidden relationship amongst the variables and the observations that we collect. And the observations, you see, collected using a statistically sound sampling technique, right? But what happens is, in practice, usually what happens is when you're dealing with something like with multiple linear regression, like it's kind of common to find like a relationship amongst the independent variables, right? And in such a case, when that happens, then we see a high correlation, usually around maybe higher than 0.6. I think the best thing for you to do is just to choose one of them, right? Choose one and then see the effect, and choose the other one and see the effect, right? But just choose one, not two. And then the third is normality, right? I guess it's kind of tied to the independent observations, and also this one as well. We're assuming that the observations essentially follow a normal distribution, right? That is a Gaussian distribution, bell-shaped curve, right? And then the last but not the most important, when it comes to linear regression, we assume that there's this relationship between our predictor and our independent variables is linear, right? So let us now jump into defining all these terms that I've been mentioning. All right. So what is regression, right? So regression essentially is fundamental area of machine learning, and regression problems are encountered in a diverse problems, right? Regression problems are essentially encountered in a diverse range of applications, such as time series analysis, control and robotics, optimization, and deep learning applications, right? So now let's give you an example. I think I just jumped the gun, but let me give you an example. We have a database of employees, right? Records at a company called X, and we want to create a system that determines salary fairly, right? A fair system that can determine an employee's salary, right? And now this is a database table. First column is just arbitrary ID, the age, and the gender, experience, and the salary. So essentially, we want to determine what is the salary of this, and then we want to use the data that we have here to determine the salary, right? So now let's kind of break it down. So now from here to here, like these are all called variables, right? In your column, if you've dealt with R before, or data analysis, these are tidy data. These are all variables in your data set, and then the rows are essentially observations, right? So these are all the observations that you go across the rows, okay? And then the employee ID, like I said, is just a column that's arbitrarily assigned to each employee, and it's essentially just the index or ID for our table, right, for each observation, right? And then we have now independent variables or features, 1, 2, 3, right? These are the features of our what we're trying to determine determine the salary, right? The features of our employees, right? This is also a feature, but the reason why I've selected this one is because this is the one that we want to determine, right? And this is our target, okay? So we're going to use these features to determine our target, okay? And then essentially, our regression is essentially a formula that we are trying to find our salary using this regression function. that takes in the age, gender, and experience. If we're to generalize this, we have a output, right? A dependent output that is a function of our independent variables, right? So this is a dependent variable, independent variables, and the regression is just a function that maps our independent variables to our dependent variables. Okay. So let us begin. So regression model is essentially a linear combination of independent variables, right? However, the variables themselves do not have to be linear. A regression model can take any form, but the linear combination, which is commonly used, is powerful enough to model most of the systems that you come across in practice. Linear regression can be referred to as essentially just fitting a line to data, or the list squares method. A regression model, right, predicts a system's behavior by extrapolating from previous outputs when the system was given known input values, right? So a straight line is the simplest regression model with the mathematical form of y is equal to mx plus c. We'll get there now. Note that all parameters are not equal during model development, and we discover how much influence each independent variable has in determining the dependent variable, right? So let us begin. So now I'm just going to plot this for you. So this is our axis. We have our dependent variable on our y-axis, and we have our independent variable on our x-axis, right? So then now we're trying to plot the relationship between these two, and if we see this increasing line as we increase our independent variables, we see an increase in our dependent variable. This is known as a positive relationship, right? And then this is the converse of this. Think of let's look at a quick example would be if you were to increase the number of hours you spent at the gym, right? You would see you should see an increase in your strength or your fitness level, right? So that is one positive relationship, and this one is a negative relationship where you see that as you increase your independent variable, it really results in a decrease in your dependent variable. And one would think of this as being an increase in your calorie intake, right? Would cause a decrease in your weight loss, right? So, okay, it's a bit more complicated than that, but it kind of makes sense. So you increase your calorie intake, the amount of food that you're eating, and you don't supplement that or add an increase in maybe activity, then yes, you will see a decrease in the amount of weight that you lose. Or if we were to flip it, an increase in your calorie intake, and you don't do any gym or anything like that, you would see an increase in your weight gain. Okay, so yeah. So now let's move to here. So now we are going to, these are essentially our observations, right? We're going to plot them on this table, and we see that these ones are our observed values. And what we want to do is get a line that best fits this data so that we can use this to predict our dependent variable given some x value, right? And this line is usually referred to as the regression line. And these are the regression variables, right? Predicted predictions, right, of our independent values. And then what happens is the distance between the observed and the prediction is essentially referred to as your error, right? We'll get more into that as we continue. So now let's look at this example where we're trying to define our years of experience and use that to determine the salary package that we would get. So now here is our regression line, and to get this line, we're going to use, this is our predicted value, right? Y hat is usually referred to as predicted value, and Y0 and B0 is usually referred to as our coefficient, and our intercept, rather, sorry, our intercept, and the B1 is essentially the model coefficient that determines the increase in that determines essentially the effect of the independent variable on our dependent variable, right? So where, yes, our model response is y hat, it says y pretty, but it should be y hat, same thing, right? Is the predicted value, and B is the intercept, and B1 is our feature coefficient, simply referred to as the gradient, and X1 is, or X is our system input or independent variable, right? And B1 is this gradient, and B0 is where our regression intercepts our y-axis, or the axis that represents our dependent variable. All right, so I will show you how you derive these, but essentially this is what simple linear regression is all about. and yeah, calorie intake and weight loss. So now you see that you're increasing your calorie intake, and then you have a reduction in weight loss, right? Here we see a negative gradient occurring. Same principle. This is our model intercept. This is our feature coefficient. And we have our independent variables, which is the inputs to our system. Right? Remember the function, you can just think of the regression as a function or a system. And we're trying to use this system to predict future values based on our independent variables. Yeah. So in simple linear regression, right? This is, I know I used B1 before and I'm using A, but yeah, it is part of the same thing. So it means the same thing, right? But let's continue. In simple linear regression, we find the relationship between one independent variable and the system's response. And where you see the independent variable is usually referred to as the predictor variable, right? And where's our independent variable is usually X, right? So we use this to predict our dependent variable. And the output is usually referred to as our model's response, right? Or the system's response. And we make the assumption that the system that we want to model is linear. Remember the second slide where I told you that linearity is one of the assumptions that we make, right? So the first step is to actually determine whether or not the relationship between the two variables is actually linear. And what you should do is usually you plot the variables against each other, and the independent variable is plotted on the x-axis and the system response is plotted on the y-axis, right? Which is what we did before. And now we determine if our system is linear or not based on the plot, right? So and we saw that that was the case. Yeah, we had kind of a linear relationship, somewhat linear relationship, as you can see that as our independent variable is increasing, we can now see that there is an increase in our observed values, right? So let's continue. Okay, did I jump the gun there? Yeah, calorie intake, and then simple linear regression. Now, how do we evaluate evaluation of the regression model, right? So we use residual analysis, right? So like before, we plot our values and then we fit it with the regression line, and then that's our predictions. Then we find our errors, and these errors are referred to as residuals, right? So a residual is essentially the difference between the actual measured value, right, and the corresponding values on the regression line, or simply the difference between the model's the known value and the model's prediction, right? So the residual values greater than 0 indicate that the regression model has predicted a value that is smaller compared to the actual measured value, and the residual values less than 0, right, indicate that the model has predicted a value that is greater compared to the actual measured value. So a well-trained model should tend to over-predict as much as it under-predicts, right? And this ties to our first assumption that we have homogeneity of variance within our prediction error. Okay, and so that's the residual y observed minus that. Okay, and then so back again. So now this is our dependent variable, right? So this is our y. Now we plotted it on our x, and we're looking at our predicted values. So we're trying, this is now the residual plot, right? So from it, so what happens is we visualize the residual of the models, right? And what we want is we want to see a normal distribution around the 0 or well-trained model, right? So the regression problem is simply trying to optimize the sum of the squares, and we'll get into that, of the residuals. So we're just plotting our residuals there, and we should see like a normally distributed. There's no relationship here. We shouldn't see that, oh, this is increasing as we increase our dependent variable, or this is decreasing as we increase our dependent variables. Okay, so now that we've spoken about all of this, now this plot is from Python, and we will go into Python later, but I just wanted to show you this so that you have a kind of an understanding of what's happening. So this is a summary result of a linear regression model. And the first thing we should look at is the coefficient, right? This over here. So this is our constant, which is our B0, and this is our feature coefficient. You can see the two values there. So the estimated coefficient values of the fitted regression line, right? So that's how you read that. This is your B0, B1, or A0, A1. And then depending on how many